Um, looks like we got a few people here, so that's awesome.
All right, should be working now.
Awesome. All right, so yeah, thanks for coming through, guys. I understand, stuff is pretty, I think a lot of people are getting burned out on the online events, so appreciate you guys sticking with us and coming through today. For those of you that don't really know too much about us, we're quantum computing at UCSD. We're not even a year old yet, and we have not even had a true in-person event, official in-person event yet. So, we're still just getting started and trying to build up and figure out our logistics and everything. There's about, I want to say like 8 or 9 of us. We'll probably grow that a little bit pretty soon here, because we're going to need some more people coming up. So if you guys check out our GBM this quarter, there might be some opportunities to get involved. And yeah, this is our kind of intro workshop. We've been trying to kind of refine this and try and give you guys a nice experience, a nice little introduction to a little bit about what quantum computing is, a little bit about what's going on with this industry, why it has so much promise, why people are saying that it's going to be the next big thing. There's the quantum revolution that people talk about, right? We'll try and give you guys a little bit of understanding as to why that's going to be the case, or people think that's going to be the case. And yeah, just give you guys a nice little overview. So I'd like to start out with a little bit of news, actually. Because there's been a lot of things happening lately in the last 3 months or so, a lot of headlines in quantum computing. So we're going to try and explain a little bit about what these things mean, what a qubit is, why a benchmark is significant. Put Google's goal in the bottom there in context. So let's get started on that one. So first of all, so IBM announced their new quantum processor called their Eagle processor. It has 127 qubits. We'll explain a little bit about what a qubit is and why the amount of qubits is significant. But at least for now, you can kind of understand a qubit is a little bit similar to like a classical bit. So your supercomputers or whatever, their performance is measured in like petaflops or teraflops or whatever, right? It's operations per second, and then those are bits being kind of filtered through that processor there, right? A qubit is kind of similar in that the more qubits you have, the more things you can do, the more processes you can do. And we'll talk about that a little bit later. But that's a big benchmark. This is the first quantum processor that's had over 100 qubits. The second piece of news was actually really recent. It was the other day. Sandia National Laboratories, which is they're doing a lot of quantum computing, like basic research. They rolled out a new benchmark for measuring the performance of a quantum computer. We'll talk a little bit more about why that's significant. But the idea is, there's a lot of different companies and different research groups that are doing research into the quantum computing, and they all have kind of different ways of saying, how good their computers are, or how powerful they are, right? Like, for example, there's this 127 qubit processor, and the question is what does that mean? Like you could easily claim to have 127 qubits, but you could have 127 qubits and have them be really low quality, and have them not be coherent. We'll talk a little bit about what that means. Or you can have them be really, really high quality error corrected qubits, right? And again, we'll talk a little bit about that means as well. So having a new benchmark that they established really is going to help us figure out which companies are actually creating the most powerful functional computers, and not just the ones with the most qubits, right? So that's something that's significant. The third thing is, I think this is the biggest quantum computing merger that we've had so far. So this is Honeywell Quantum Solutions, which is a pretty big pretty big little division of Honeywell, and they've been developing this division for a while. That's a kind of hardware division. So they do quantum computing hardware with something called trapped ions. If you guys are interested in that, we actually have a hardware workshop coming up. But that's a company. They've been doing some really interesting work in quantum computing hardware. And then Cambridge Quantum is a company that makes quantum computing software. So they're kind of a level up, kind of step back from that hardware. And those two companies merged together, and their new name is Quantinuum. I believe it's still technically kind of a subset of Honeywell, but I think there's rumors that company's going to go public. So a lot of investors are kind of really excited about that. So that's some really interesting news there. The last one is Google just kind of released its kind of, I guess, just a review of the last year. And in that review, they talked about their goals for the next decade. And they think that they're going to have a practical quantum computer, a quantum computer that can do stuff that, is intractable on like a supercomputer. They said they say that they're going to have that goal. They're going to complete that by 2030, the next 9 years or so, or 8 years. So we'll see if that happens. A lot of these companies set really kind of unrealistic goals, but it is very exciting to see a company like Google, who is perhaps the biggest industry leader right now, setting that high of a bar. So that's pretty cool. So that's a little bit of kind of news to kick us off, and we'll talk a little bit more about the significance of this stuff and help you understand, kind of put in context what all this stuff means. But yeah, that's just a little bit of news for this industry. And if you're on our Discord, you'll I try and post stuff like this all the time. That whenever something comes out, some new news comes out, I'll try and post that in news on the Discord as well, so you guys can stay tuned for that. But yeah, that's the latest headlines there. So let's just kind of take a step back, and we also went over this a little bit in the last workshop, but I think it's significant to put it here because it's a good overview of why quantum computing is significant. So the first thing would be faster search algorithms. So there's something called Grover's algorithm that's been proposed for quantum computers, and having that faster search algorithm than a regular computer is going to allow us to do stuff like quantum machine learning, that is, and run these algorithms faster than we could on a regular computer. So that's really promising. We also have more accurate simulations. So something like a molecule or a protein, for example, is a quantum system, right? It's a system that, has, instead of having discrete kind of existing in a discrete way, we're talking about systems that are kind of fuzzy, systems that are, probabilistic, that are not, that can't be modeled necessarily on a regular computer that deals with ones and zeros. So the qubit, which we'll talk about a little bit later, gives us the ability to simulate things, simulate quantum things in a quantum way, and that's going to, a lot of applications for quantum computing focus on, for example, material and drug discovery that can be enabled by this better, more accurate simulation. So that's really exciting. We also have faster prime factoring. There's something called Shor's algorithm. In fact, ACM has ACM Cyber is collaborating with us to bring you guys a workshop. I think this is going to be this coming Monday here. They'll talk a little bit about this cryptography stuff. But basically, this thing called Shor's algorithm is, if we can create the hardware that is required to run this, it would actually be able to factor prime numbers faster than a regular computer would be able, like a supercomputer. And this would enable us to break cryptographic keys using a quantum computer. We'll talk about that a little bit today, but that's mostly going to be covered in our upcoming workshop with ACM. And then finally, having more secure communication could be enabled through through a phenomenon called entanglement. And again, I think ACM's workshop will talk a little bit more about that. They'll go into depth as to how you can encrypt information using quantum computing, but that's a big application. That's the application that that China is all in on, because they got totally, at least the story is that they got totally freaked out by the whole Edward Snowden thing and the NSA snooping, and they want to use quantum technology so that the U.S. government can't steal, the NSA can't steal their secrets. And so they're spending billions and billions of dollars on trying to create, quantum cryptography, so that they can have, this theoretically perfect encryption of their data. So that's just a little introduction to the applications of quantum computing, what people think that we'll be able to do with this technology once it matures a little bit more. And then I just wanted to talk about a little bit about the origins of quantum computing. We won't go too far into depth here, but I just wanted to say, just emphasize how new this technology is, right? It was only in 1980 that this technology was proposed, right? So quantum physics has been around for over 100 years, but it was only in 1980 that this idea of using quantum physics to do computing or simulation was even proposed. So that was, very, very recent. And it wasn't until 1998 that an actual quantum computer or a quantum computing system was developed. I want to say that had something like 3 qubits. So it's a really basic system. But even that was a huge technology challenge, took 15 years to develop. So this is a really, really new field. I think a lot of you guys might even have been born before 1998, right? So this is something that in our lifetimes has kind of gone from non-existent to a kind of fledgling industry here. So it's really exciting, how new this field is. And then the people you see here, these are some of the big players in this industry. So you guys have probably heard, or maybe heard of Richard Feynman. He's a really famous physicist. He was one of the pioneers of this industry. But also David Deutsch and Paul Benoit both had huge impacts early on. And Peter Shor, who's known for something called Shor's algorithm that we'll discuss a little bit later. So let's go back to this. Let's see, the first item here, right? They have their IBM proposed their 127 qubit Eagle processor. So we're going to talk a little more in depth about that. You can see this chart on the top right here. It says scaling IBM quantum technology. So you can see it says 2021. It says 120 qubit, 27 qubits Eagle, right? So this is IBM's kind of. They came out. I think this was last year that they about a year ago that they put together this little chart here. And so they said that they're going to have their Eagle processor by 2021. And it turns out that they actually they kind of said at the end of 2021 that they had the hardware capability to build the Eagle, but they actually haven't built it yet. So they're a little bit behind in this projection, which I think is normal for a company like IBM, being super optimistic and thinking they're going to be able to do all this crazy stuff. And you can see, like 2022, they say they're going to have their Osprey processor, which is going to have 433 qubits. I think it's pretty unrealistic that by the end of this year they're going to have 433 qubits. They might not even have the Eagle fully developed by the end of this year. So it's interesting to see how this projection is starting to fall apart a little bit, but also that it's not totally off, right? The Eagle is definitely within reach. So this is kind of exciting. Right now, we're in what we call NISQ, or noisy intermediate scale quantum computing, which means basically, first of all, we're not at the point of applications yet, right? We're not doing anything really useful that like a regular computer can't do. Quantum computers have done stuff that regular computers can't do, which we'll talk a little about later. Something called quantum supremacy. But for now, quantum computers is still in kind of in the research phase and the kind of R&D phase in industry. But it has been growing really, really fast. So again, we'll talk about what a qubit even is, but we had 3 qubits in 1998. That was that first quantum computer that we were talking about. 2011, we had 14. In 2019, we had 53, and now this year it seems like IBM might succeed at creating a processor with 127 qubits. So that's only in 2 years. We've gone from, or 3 years, we've gone from 53 to 227. So that is very exciting. Seems like that's been kind of an exponential growth. And then you can see that chart on the bottom right. That's also IBM's their backends. So that's the actual physical quantum computers that they have that you can access through the cloud. The amount that they have has been growing exponentially, and the amount of qubits in each of these backends has also been growing. So you can see those colors, right? The qubit QV4, right? That second color from the left there, that would be like I want to say a 4 qubit processor, right? So it's less powerful processor. Now we have these like QV64, QV32. We have these more powerful processors now. So that seems to be growing exponentially. So that's super exciting. Even in just like a few years. So, I guess let me check the chat real quick, see if you guys have any questions. Or let me share the result of the poll first for you guys. How do I do that? Never mind. Let me just check the chat real quick. Yeah, so we'll quantum entanglement communication attached to traveling photons. Yeah, that's something that that ACM workshop is gonna cover. So if you guys should totally check that out. That's really interesting stuff. We're on an email on time. Yeah, exactly. So it looks like we got that's the chat there. So let's go ahead and continue. Let me take a little breath for a second, have some water, and then we'll get going. So we talked about qubits, but we didn't really explain what a qubit is. So I'm going to try and give you guys a little bit of a background on what a qubit is, what that means, and what kind of the implications of that are. Understanding what a qubit fully is something that I think is probably beyond the scope of this workshop. Something that's a little more tricky to understand. You need a little bit of linear algebra and some a little bit more understanding of quantum physics. But I think I could probably give the explanation that I've been trying to cook up for you guys. I think is sufficient to at least give you guys a little bit of an intuition as to what a qubit is. So, in classical computing, which is our just regular computers that are smartphones and our laptops and stuff, right? Those use something called bits. So I'm sure a lot of you guys have heard of a bit, right? A bit is something that whatever the hardware is, if it's a MOS capacitor or transistor or something like that, it basically stores a piece of information in the form of either a 0 or a 1, right? You have 2 states, and every computer on Earth pretty much stores information as one of 2 states, right? A 0 or a 1, or a high voltage or low voltage, right? That's kind of how what we call classical computing works. And so, if you want to store, a number or a decimal or floating point decimal, something like that, right? You have to figure out how to map that onto like 1s and 0s. However, a qubit is something that's a little bit different. There is actually an infinite amount of states that a qubit can exist in. So a qubit, like a bit, can exist in a 1 or 0 state, right? So you can have a qubit that is the same exact thing as a bit, right? It can be a 1 or a 0, but there's also an infinite amount of states between 1 and 0 that qubit can exist in. So we'll talk a little bit about what that means. The second point is just like a bit can be, can be any physical object that can exist in a 0 or 1 state, right? So I think right now, I think it's MOS capacitors that are generally used to store bits. but we can also use transistors. There's optical implementations. There's like optical computing where you store a bit as in a form of a photon, right? So there's a lot of different implementations, and the same thing is true for quantum computing. So we have our quantum computing hardware workshop coming up. Let's see, that's going to be 2 weeks from now on the 21st. We'll talk a little bit about what a qubit is physically, and how different quantum computing companies store these qubits. That's something that's really interesting because there's a huge range of different systems you can use to store a qubit. Same thing with like a regular computer, right? There's many ways to store an actual classical bit, right? So so you guys can check out our hardware workshop for that. The third thing we'll talk about is the Bloke Sphere, which you might have seen, that thing on the bottom right there. You can see that there's a little, it says qubit, basic unit of quantum information, right? The thing on the right there, that is the Bloke Sphere. And that's a mathematical kind of geometrical representation of the mathematical object that is a qubit. And so we'll talk about a little bit about what the Bloke Sphere is, and how that stores that information there. So what I'll do is try and give you guys a little bit of an intuition on, what a qubit actually is. So let me do this. Let me turn my video off. So let's see, stop video. And then I'm gonna write a little bit of something for you guys. See if this helps you guys understand what the heck the qubit is. So let's first of all, have any of you guys heard of like Schrodinger's cat? I know it's, you might have just kind of heard that in passing. Any of you guys know a little bit about what Schrodinger's cat is? Maybe you've read about it a little bit, right? Because I think that's a good place to start. Maybe I have, maybe I haven't. Exactly, right? So Schrodinger's cat is kind of the classic illustration of something that we call superposition in quantum physics. So the idea behind Schrodinger's cat is you have a box, right? And of course since you have a box and you have a cat, the cat goes in the box, right? Because anyone who has a cat knows how much cats love boxes. So here's our cat, right? And you also have a radioactive isotope of, I can't remember what it was. I want to say like barium or something like that. And that radioactive isotope has a 50% chance of decaying, right? And that actually is a quantum system there. And this is kind of a microscopic quantum system here. And so what this thought experiment does is it says, okay, well, let's say you have a detector here, right? And that detector is connected to a vial, right? And that vial contains a poisonous gas. Or let's say a sleeping potion, just so we don't have to kill this cat, right? And then this sleeping potion gets released if this isotope here decays. And so the idea is this decaying of this isotope, this is a probabilistic system, right? So this system, when you don't observe it, so this is kind of one of the general concepts of quantum mechanics, and it's something that's very, very strange. But when you don't observe the system, right, when you take this isotope and you put it in a box and you don't observe it, that isotope, it doesn't decay and it doesn't not decay. It exists in something called a superposition state. And this state is a really strange state because it's not really a mixture of both, but it's also not either. It hasn't decayed and it hasn't not decayed. It's something that I'm not sure is even really understandable conceptually. A lot of quantum physicists themselves have said, there's the famous quote from Richard Feynman, right? If anyone who thinks they understand quantum physics does not understand quantum physics, right? It's just a very, very kind of baffling behavior here. And then once you observe this thing, right, once you hook up a detector or something like that and detect whether this thing has decayed or not, then we say that at least one interpretation of it is we say that wave function collapses. So there's also different interpretations. There's like the Everettian interpretation, the many worlds theory, that says instead of that wave function collapsing, it says that the universe itself, splits into two. One universe for that not decaying and one universe for decaying. However you want to think about it, right? It's really baffling behavior that this thing, doesn't exist in one or the other state until you observe it. And so Schrodinger's cat is kind of saying the same thing, as long as no information is getting in and out of this box, that the actual state of this box itself and the cat's either being awake or asleep from this gas, right? That state itself is actually exists in this superposition, which is really kind of strange concept, right? Is this cat is not fully dead, right? And it's not fully alive, and it's not really like half dead and half alive, right? It's kind of a strange in-between state. And so, obviously this might not make sense to you guys. I'm not sure if it even makes sense to physicists, right? But I just want to introduce you to how weird quantum physics is, because it's I think a really good way to kind of think about a qubit. And so this, in a nutshell, is what a qubit is. And so I'll kind of go over a really quick kind of simulation, or a quick kind of analogy that is usually taught in textbooks. But that's, in a nutshell, basically what that is, right? A qubit is a quantum system that exists in one of two states, and a superposition of those two states. And depending on how you set up that system can exist in a whole spectrum of different states. So I'm going to go over and show you guys the Bloke Sphere here. So this over here is something called the Bloke Sphere. And it's basically just a way of representing the mathematics of a quantum system, of a qubit. So right now, this Bloke Sphere is up, the spot that we're at is at the top here. So this would be, let's say this would be the cat being alive, would be this top state here. And then on the bottom of this Bloke Sphere would be, let's say, the cat being dead here, right? And you can actually adjust where you are around this sphere, right? So you start out, the cat's alive, then as time goes by, the probability that radioactive isotope decays increases, right? Now here, you're in your kind of 50-50 state, so that cat, there's a 50-50 chance that cat is alive, that cat is dead, right? And then as that system evolves, eventually you get to the point where there's 100% chance that cat is no longer with us, right? So if you wait long enough for that radioactive isotope, there's 100% chance that it's going to decay, leaving you at the bottom of the sphere. So this is just kind of a representation of the mathematical object that is a qubit. It's not necessarily something that is you can totally understand conceptually, but this just happens to encapsulate the math here. And we will have some events in the future that will deal with the actual math behind this. This stuff over here with this cosines and sines and the e to the I phi and all this stuff here, right? Don't worry about that for now. But we'll have some stuff coming up, hopefully in person at some point, to teach you guys a little bit more about what the actual math is behind here. There's also something called a phase. And we won't worry too much about that. I might explain if I have time. I might explain a little bit about what a phase is, but either way, this is just a little added complication that also exists that I guess you just kind of be aware of, right? Is that it's a little more complicated, but that's kind of the gist of it right there. And then finally, I just wanted to talk about a couple other ways of thinking about a qubit before we move on, right? So the first way is something called an interferometer. So this is an optical device, and we take light, and right here we have what's called a half silvered mirror. So that means half of the light's going to pass through this mirror here, and then we're going to reflect it off a regular mirror, and it's going to go up here. And then the other half of this light is going to get reflected off this half silvered mirror, and we're going to reflect it again, and it's going to go this way. And what we can do is we can take two detectors and set them up like that, right? And we can detect how much of the light goes up and how much of the light goes let's say in the down path, right? So obviously, if we just take light, which is a bunch of photons, we shine it, half that light, half that intensity is going to go here, half that intensity is going to go here. But the question is, what if we take one single photon and we shine it into this device here? Well, one photon is indivisible, right? So photon is the fundamental particle of light. So I can't, my photon can't physically split into two, right? I can't get half a photon going up, half a photon going to the right. So what's going to happen is I'm going to actually have a probabilistic outcome. So half of the time my photon's going to go down, and half the time my photon's going to go up. So kind of a strange concept. And the trick to it is just like Schrodinger's cat, if I get rid of detectors, then I'm actually going to exist in the same kind of state as before that we're talking about, in a superposition state. So if I pass one photon through this thing, that photon is actually going to turn into a superposition. So there's going to be some probability the photon's going to go this way, some probability the photon's going to go this way, right? It's going to be 50-50 chance there. And that state that photon's going to exist in before I measure it is going to be a superposition state. It's going to be this kind of weird Schrodinger's cat, not up nor down kind of state. And so we can, again, represent this with the Bloke sphere. So if we pass one photon through here, right, that photon is going to start out in a definite state, right? And then it's going to go into a superposition. And depending on how we adjust that mirror, like we can make that mirror more reflective so that that photon's more likely to go up. That's going to change our probability here, right? So we can go around the Bloke sphere depending on that. And in fact, that actually gives us a way of thinking about phase as well. And this is a little more advanced, so don't worry about if this doesn't make sense. But we have our photon, and that photon is a light wave. So it's like we can think about it like a cosine wave, right? Let's say that the part of the photon that goes up and the part of the photon that goes down, those are what we say in phase. But what we can do is we can put maybe like a piece of glass or something in the middle here, and we can adjust the phase of only one of the paths. So what's going to happen is this, let's say this bottom part here is going to get out of phase with the top part here, right? So let's say we're here, right? So that's going to lead to a phase in this Bloke sphere. So as you see here, right, that phase can be adjusted. So for example, right, like this would be, what would this be? This would be a pi/2 phase shift here, right? So that this would be, as we go around our unit circle, we start out here, right? The bottom path is going to start out here, and this phase difference here is going to be pi/2. It's a little more advanced. Don't worry if that doesn't make perfect sense to you guys. But I just wanted to introduce that as well. So yeah, hopefully, maybe I'll give you guys a second to let that sink in. I'll check the chat, see if anyone's said anything. But I'll let you
Hey,
guys.
I have a question.
Yeah, go for it.
So like the cat thing, I saw some videos about the double slit experiment. Is that the same kind of concept that where they were in two states, or is that kind of different?
Actually, that's actually a great question, because that is in fact essentially the same concept. So like, let's say I have two slits here, and I take a photon. Well, first of all, I can just shine light in general through these two slits, right? Half the light is going to pass through the top slit, half the light is going to pass through the bottom slit. I'm going to get some, interference pattern on the wall across here, right? But the question with this one is, what happens if I just pass a single photon through these two slits? Well, like classically, what's going to happen is the photon's either going to go through the top or the bottom, right? But if I put this whole thing in a box, right, and I don't observe it, just like Schrodinger's cat, right, and just like this interferometer thing that we're talking about, right, this photon is actually, there's going to be some probability that it passes through this top slit here, and there's going to be some probability that it passes through this bottom slit here, and those two probabilities, this is again a little bit more advanced stuff, right? But those two that kind of splitting there, those two kind of versions of the photon, right? Photon V1, I guess, and photon V2, right? Those are actually going to interfere as well, and we're going to have what's called a single photon interference pattern. And I, again, getting a little more advanced, right? But if we actually open this box and we observe this photon here, this interference pattern is going to collapse, right? This thing is, at least that's the Copenhagen interpretation, right? Is that this thing itself is going to collapse, and we're going to actually get only one of these. We're going to, let's say, get V1, and then we're actually going to observe just a single point like this instead of an interference pattern. So a little bit kind of trickier idea, but that is the exact same concept, actually. So great question.
So I have I don't know if you have time, but I have another question that builds on that.
Oh, yeah, maybe if you don't mind asking at the end, I'll stick around for a little bit, but I think we got about 15 more minutes until 5. So maybe if you don't mind me just finishing up real quick, and then I'll get right to your question though after.
Yeah, of course, no problem. Thank you.
But yeah, that's a great question. All right, so sounds like that's the only questions we have. I'll check the chat real quick, see if there's anything else. Looks like that's good. All right. So hopefully that gives you guys a little bit, of an understanding of what a qubit is, and like what it means to be in a superposition, how this kind of Bloke sphere works a little bit, right? These again are really tricky concepts. Takes a little bit of math and some understanding of quantum physics to understand them like fully, but hopefully that gives you guys a little bit of an intuition. So we're almost done here. I'm going to turn it over to Thomas pretty soon here, and he's going to kind of help me finish this out. But before that, I just wanted to talk a little bit about what the parent science of quantum computing is, which is quantum information science. And talk about how this whole field is a little bit more broad than just quantum computing. So quantum computing is kind of, gets the limelight. It's definitely the most hyped kind of subset of this field. Everyone's talking about quantum computing all the time. But it turns out that quantum information science is the kind of parent science of quantum computing, and contains a lot of other stuff that is not just contained in quantum computing. So I'm going to talk a little bit about that. And in fact, a lot of experts think that quantum information science is the follow, and that quantum computing is just a subset. It's something that gets a lot of hype, but that quantum information science itself contains a lot more kind of substantive stuff that's going to be, is going to mature as a technology faster. And so we'll talk a little bit about that. So first of all, we talked about quantum computers being used for quantum simulations. You can actually do quantum simulations with different systems that are not technically quantum computers. So for example, there's things called like optical lattices, where you can take light waves and you can create like these kind of lattice like structures, and you can put atoms in like a geometric arrangement, kind of crystal-like arrangement, right? And you can use that lattice that you can control to simulate more complicated systems that look similar. So you can take, you can make an optical lattice in kind of a diamond lattice shape, right? And you can simulate what an actual diamond crystal, which is more complicated, would do. So there's different, and don't worry if that doesn't make perfect sense to you guys, right? But just kind of trying to introduce you to the idea that there's a lot more stuff you can do within quantum information science that's not specific to quantum computing. So, for example, you can create a little kind of lab simulation of like a chemical reaction. That you can create a system that has similar behavior, but that's just more simple and easier to control, right, and easier to observe. Same thing with protein folding, drug interactions. You can create these little simulations that are not really quantum computers, but they kind of behave similar, right? They're much easier to control. The second thing would be quantum communications, that we talked earlier about that. There's the eventual goal of a quantum internet, which would definitely interface with quantum computers, but is a little bit of a different kind of technology, right? It's a little more broad. And then finally, a big field right now is quantum sensing. So like being able to detect, a single photon, for example. I did an internship last summer at a lab, and they were using, single photon counters, and those are using, quantum sensing. You can't use a regular sensor to detect single photons or, tiny perturbations in, a laser, for example. Like if you guys know a little bit about like what LIGO is, that is the gravitational wave observatory. That's how they detected the first gravitational wave that we've ever detected. That's kind of quantum information science. That's quantum sensing. It's using lasers to detect tiny, at atomic scale changes in the length of between two points that is caused by a gravitational wave, like like really crazy advanced stuff. But that's more quantum information science than quantum computing, right? It's a little more broad. So I just want to bring up those, kind of expose you guys to those, see if that interests any of you guys, because that's something that is a more broad technology, and that might mature a little bit faster than quantum computing, which might be, quantum computing might be 40 years off. Whereas, we might be able to do quantum sensing, in 10 or 20 years. You might have quantum sensors in your phone, right? So that's a pretty cool technology there. So I'm going to turn it over to Thomas. He's going to talk a little bit about kind of what governments are doing right now with quantum computing and quantum technology. This is something that's a little bit of a review from the last intro workshop we did. So for those of you that saw the last one, you might see some new stuff, or might see some of the same stuff you saw last time. But we'll try and keep it a little bit fresh, and give you guys a little bit more context. So go ahead and talk to us a little bit about what governments are doing, Thomas.
Yeah, sure. So we'll start off by talking about the National Quantum Initiative. That's the US government's the big act that they passed in 2018 to fund quantum information science. See there, it says $1.2 billion, which is, as a lot of people would say, a lot of money. And it's a very broad bill. It funds just about anything related to quantum research. And that, that goes so far to, there's plenty of people doing research on things that are not really like quantum related, in the sense that who knows if they could actually be applied to a quantum computer or even quantum information science. But if there's any little way that the researcher can word their research as being quantum related, they'll do it. And this comes from a professor I was talking to who was telling me this. They'll do that just so that they can get the funding from this act, because they are really just shelling out as much money as possible to incentivize people to research it. So just as a little aside, if you're thinking about quantum computing, or quantum information science, there's definitely many years of expensive school to get there. But once you're doing the research, there's a lot of money out there for funding, which you can't say for a whole lot of the fields. Can you go to the next slide, Ben?
Oh yeah, sure.
Okay, so next we'll talk a little bit about China. As Ben sort of talked about earlier, China recently, I mean, not that recently, a couple of years ago, had this sort of quantum, this like satellite that's built into their quantum like photonic computer. And with that, they were basically able to transmit to like entangled photons thousands of miles apart. And the whole world is a little bit freaking out about it because in terms of the like quantum communication, China is sort of far ahead of everybody else. As you can see there, sort of that bottom bullet point, the biggest spender on quantum computing from 2012 to 2017. So, you know, the US and Europe are, they're putting money into it, that $1.2 billion, but they're definitely lagging behind in terms of China for how long China has been putting money into it. And next slide, please. And then just like some other stuff from other, you know, random tidbits. President Biden said something in March that he was saying that they're going to be putting closer to 2% of the GDP into science. It's about 0.7% now, so almost a 3 times increase, and mentioned quantum computing specifically by name. Australia, UK, and the US have all joined this like AUKUS, which is this basically agreement that they're going to share a bunch of tech amongst each other and jointly work on a bunch of things. If you ever heard about the like submarine fiasco that was a few months ago, this is what it was. The submarine was just like an extra thing that was also happening, but included in it was they were talking about working together on quantum technologies. And then the quantum technologies flagship is the EU's version of the National Quantum Initiative. And they also put about $1.2 billion towards quantum QIS research. So here's a slide sort of talking about quantum supremacy, which is a term that we've thrown around quite a lot during this presentation and haven't really defined it. And partly that's because it has a very confusing and sort of debated definition. So in 2019, Google claims that they had a computer that had quantum supremacy. And what they did is they basically built this quantum computer and then figured out an algorithm that's completely useless, but really hard in exactly the right way that this quantum computer could solve. And then they ran it on the quantum computer and said, huzzah, look, we've done it. And so it's technically true that they ran something that you can't really do on a regular computer, but in sort of the most pointless way. So there's a lot of debate going around about whether that should be actually used as a metric to show that, yes, this quantum computer is so powerful. And so that IBM has their own measurement system called the quantum advantage. And that's what they think that you should be measuring these quantum computers on. And, you know, there's obviously some corporate like shenanigans going on where they have their own interest in saying that the other one isn't actually as good as they claim. So there is definitely some confusion over what there's no standard metric, I guess is what I should say, on how we measure quantum computers. But there was a recent paper that came out that was proposing one.
Yeah, I guess let me just add real quick as an aside. That was one of our first little headlines here, right? We said Sandia National Laboratories, they have a new benchmark for measuring performance. So that's kind of a way of maybe getting around that and having like a standard benchmark so that, you know, Google can't just claim whatever they want to claim and have it be this whole controversial thing, right? If we have like a consistent benchmark, then that lets us kind of, you know, judge these different quantum computing companies and see which one actually is going to be able to do the most useful things, right? So that's kind of a I guess exciting for the field there that we have like this new benchmark.
Yeah, so only like a couple more slides here. So this one's just sort of talking about the challenges, and this is more catered towards specifically the super cooled Josephson junction quantum computers, um, which is the main type of hardware. But there's sort of a few problems. One, they're really sensitive, and really sensitive to a lot of things. So, you know, like it says thermal EM, acoustic noise. It's even to the point that there's like a quantum computer in Fermilab, which is outside of Chicago, and there's some highways that are like a few miles away, and sometimes the noise from the highways being a few miles away and like the very small vibrations sort of ruin the experiment, and they can't use it. So even that level of noise is disrupting to quantum computers. You have to get them really cold. These super cooled computers are basically in like the coldest fridges we can make. And there's a huge other part of the quantum hardware that's completely independent from the actual processors, and it's just about building better fridges to get them even colder, more efficiently. And yeah, so storing qubits is very difficult. You have this thing that probabilistically decays into different states. How do you get it to stay in this one state? Imagine it's like your RAM just randomly wipes, and anytime you want to do something, you're like, oh, I'm gonna open up Zoom. Sorry, your computer wiped its RAM and now it's gone. And there are error correction methods, but there's nothing that's strong enough to overcome how noisy and error prone current quantum computers are, which is why we're still in that NISQ, the NISQ regime, because everything we have, our error correction is sort of just very minimally helping quantum computers. And then, yeah, just sort of like that last bullet point says, there's a lot of quantum computing algorithms that aren't even written. There's a lot of quantum computing proofs in terms of proving that certain algorithms are even theoretically possible or better than classical algorithms that haven't been proven. So there's a ton of work to be done, both in the theory in terms of writing algorithms and proving like the usefulness, as well as in terms of the hardware in getting more efficient quantum computers, less error prone quantum computers, just sort of all around.
Yeah. So yeah, thanks, Thomas. Really appreciate that. Something I wanted to add about that algorithm thing is there's definitely the possibility that this whole thing will, I guess, become kind of like TensorFlow, and that you have these like really low level, really complicated quantum algorithms that PhDs are working on, but then it might be possible, maybe 20 years from now, to have some sort of library of all of these really complicated algorithms that a high school student or a beginning CS student can learn how to use to like do optimization or something like that. So that's kind of a big goal of quantum computing. That's what IBM's trying to do. We talked about that software merger, or that merger up there where Cambridge Computing or Cambridge Quantum, they do like quantum software as well. So it very might well be possible for you guys, even without getting PhDs or going into the super technical aspects of this field, it might be possible for you to learn a little bit of basic stuff about quantum computing, learn a little bit about how these algorithms work, and be able to actually just like someone who doesn't have a PhD in machine learning can use TensorFlow, right? There might be some framework that you can use to do stuff with a quantum computer without having all this PhD knowledge. So that's kind of a big kind of hope for this industry. So you guys can check out Qiskit if you're interested in that kind of thing. And let's see, someone of you guys mind dropping that link there, if you don't mind, into the chat, so you guys can check that out. Qiskit is IBM's software for quantum computing. They're actually already doing a little bit of that, where they're you know, getting a little higher level to the point where you can, you know, you don't need to know all of the details of these algorithms, and you can still, you know, use them for interesting things. So that's definitely a hope. So, you know, if you guys are interested, you can keep coming to our workshops. We have our GVM next Friday at the same time here. We also have our hardware workshop the week after. That's going to talk a little bit about superconducting transmon qubits and Josephson junctions and trapped ions and a little bit like optical chips and stuff like that. Really, really interesting stuff. If you guys are interested in physics, which is, you know, personally more kind of my kind of thing. If you guys are interested in that stuff, that will be a really cool workshop to check out. We're going to try and get some, see if we can try and get some people, maybe some PhD students or researchers to come present a little bit of their research as well. So we'll keep you posted on that. If you guys haven't joined our Discord, you can check that out. That's how we are doing most of our communication. And then this article, Quantum Computing for the Very Curious, and if one of you guys doesn't mind dropping that link as well, that's a great way to get started, kind of get your hands dirty with quantum computing, and learn a little bit about how it works with kind of a really low level of background knowledge. So that's a really cool, a really good article for just kind of getting started, to see if you're interested, if it clicks for you, or if it you know, see if it makes any sense to you guys. That's a great way to get started. If you guys are interested in learning a little bit more. So yeah, come check that out. And then I think, yeah, so we'll open it up. I think, who was it? I think Robert.
I have a question for everyone.
Can I add something real quick?
There you go.
Oh yeah, go for it.
So I was just gonna say, I'll put another link in the chat. It's for D-Waves, it's sort of to their homepage, and they have something called the D-Wave Leap, which is similar to Qiskit in the sense that if you provide them your like your GitHub, then you can get access as a quote unquote developer, and you get some number of compute time per month, and you can like build and run quantum computer algorithms on their system, which IBM's is, I'm pretty sure, like one of those super cooled quantum computers, and this one is a quantum annealer. So it's slightly different, but similar in the sense that it's another one of those tools that a company is letting you play around with their quantum computer.
And your profile picture. Oh my god. Wait,
Real
Andy,
quick, everyone, there's a feedback form in the chat. If you can fill
Yes,
that
there's.
out. So
Yeah, if
more
you guys
people
could
should
fill out the
answer
feedback
poll.
form and the poll, yes.
Only two
Those
people
are
responded
two
to
very
it.
important things. Yes.
Oh wait, only no, 6 people can answer the poll. So
Yes, because there are 4 of us.
But okay, cool, Robert. Yeah, thanks for coming. Hopefully I'll get to ask that soon. And well, we were planning on trying to do eventually we're going to try and do like a quantum computing mini course. That's one of our goals. It keeps getting kind of pushed back because everything seems to be staying virtual. But eventually that's gonna happen. So hopefully you'll get a chance to kind of dig into this stuff a little bit more at some point. I might try and host a couple like kind of informal study sessions this quarter. I did a couple of those over the summer, and they got pretty good feedback. So stay tuned for those as well. But yeah, I'll leave it open for a second if any of you guys have any questions. Yeah, thanks, Sammy. Thanks for coming.
come on, where are all the people who want to see Ben play the sax?
Save that.
It's not here.
I know, maybe at some point.
Maybe when we have an in-person GVM.
Yeah.
If we have an
When we have an
GVM.
in-person event, yeah.
Yeah. In 4
Yes,
years.
sir.
That would have been so great if we had an in-person event. Then you could bring your saxophone, and then
True.
oh, it would be epic.
Yeah. I know we had rooms reserved for all of the for everything, like all these 3 workshops for this quarter. We had like all these, we went through this whole process of like reserving rooms and getting like doing the intake forms and the tap forms and the like, funding proposal or whatever.
All right, I'm gonna stop the recording because everyone's gone.
Yeah, they're
Oh,
all
yeah.
gone.